Okay, and we are back again with series parallel circuit faults. And one more time, we are looking at faults with multiple components in a parallel branch. And this time we are going to short around R4. So I am going to start by bringing that up on the screen, and you'll see that there's an alternate path for current around R4 now. So as we know from shorts in all of our other videos, R4 is effectively removed from the circuit because there is now an alternate path around it, and so it is just R3 and R5 that will be in parallel with each other. There are still two paths for current because there is another component within the branch. Alright, so let's look at what's happening with resistance. We do have to calculate parallel resistance here because we still have two branches of current. So we'll do our resistive equivalent. And we know that originally our total resistance was 13.33K from our previous circuit. So that's our original number with everything working. Now, if we take our 5K ohms for R3 and our 5.4K ohms for R5, we get a total resistance value for our parallel of 2.6K ohms. Now, of course, we can add that to our two series resistors, and we get a total resistive value for the circuit of 12.6K ohms, which is actually a decrease from our original of 13.33K ohms. So we look again at Ohm's law. If we had a voltage that did not change and resistance that went down, we would expect our total current to go up. Now, let's look at total current. So we did have 3.75 milliamps. That's when everything is working. And of course, we don't have that now. We take our new, we take our voltage divided by our new ohmic value, and we get our new current of 3.97 milliamps. And that is indeed higher than 3.75 milli, so it went up. Let's look at voltage drops. So for R1, we did have 9.38 volts, and we take the ohmic value now of R1 and multiply it by our new larger current, and we see a slightly larger voltage drop of 9.93 volts. And again, on R2, we have the same ohmic value, but a larger current, so we see a slightly larger voltage drop. Now EREQ, we did originally have 3.33K out there. Now we have 2.6K out there. And so we are going to see a decrease in the voltage out on our parallel portion. Now, I'm throwing up the arrows for you. We just talked about them. And I want you to think again about what we talked about in the last video. So you will see that our two series resistors, whose ohmic values did not change, are following total current. So they are going up following total current. You will notice that it's a fairly small amount that they are going up because current is fairly small. It doesn't change very much. 3.75 milli is not that much smaller than 3.97 milli. And so you see those voltage drops rise, but not that much. When you look on your parallel, though, we went from 3.33K to 2.6K. So that's quite a bit ohmic value-wise. And so we went down almost 2 volts in our parallel portion of the circuit. All right, and when we look at the voltage drops out there, let's look at that parallel portion where we have one functioning component and one that is not. So if we were to put, of course, our leads from the bottom of our 5 to the top of our 4, we would read our applied voltage to our parallel of 10.32 volts. However, if we were to put our black lead at the bottom of our 4 and our red lead at the top of our 4, we would find that we read just 0 volts. And that is because there is no difference of potential there, right? There's no resistive value. It's a straight wire. And so With no resistive value, it doesn't matter what current is, you're not going to have a voltage drop. Remember, voltage is a difference of potential. But if you put your black lead at the bottom of R5 and your red lead at the top of R5, you will read that 10.32 volts because that is where the ohmic value is of your circuit. So there is a difference of potential between one side and the other of R5. Alright, and this is a short in a series parallel circuit. Next, we are going to discuss changed values.